The aim of this experiment is to study the dependence of potential difference, that is V, across a resistor on the current, that is I, passing through it, and determine its resistance. We will also learn how to plot a graph between V and I. The material required for performing this experiment would be an unknown resistance wire, a voltmeter to measure the potential difference, an ammeter to measure the current flowing through the wire, a battery, a rheostat, a one-way key, some connecting wires, and a piece of sandpaper. So we will first set up the circuit as you can see here. So resistance wires to be placed in parallel with the voltmeter. So you can see here this small wire that you see here, this is the resistance wire and this is a voltmeter which have been put in parallel. Then we have a one-way switch or a key. We have a rheostat, then an ammeter which is in series with the source of current which is the battery eliminator in this particular case. So in the circuit diagram also you can see the resistance and the voltmeter, they are in parallel. Then ammeter, the source of current, key and rheostat, they are all placed in series. Let us now perform the experiment. So we have created the setup as you can see here. So be careful about the positive and the negative terminals. The red end is the positive end and the black end is the negative end. So we have this battery eliminator here. We have connected the positive end of the battery eliminator to the positive end of this voltmeter, and the negative end of the battery eliminator has been connected to the negative end of the ammeter. The positive end of the ammeter has been connected to this rheostat which acts as a variable resistance, and then we have a switch in place through which we can control the circuit by turning it on or off. So right now I am turning the circuit off by removing the switch. This is the wire whose resistance we will be checking using this circuit. So as Ohm's law says, V is directly proportional to I. When we turn on the current in this circuit and we increase the amount of current by decreasing the resistance, you can note the readings here. So you can see the reading in the ammeter is 0.5 or 1 ampere because the least count is 0.2, so it's corresponding to 5 division, that's 1 ampere here. And if you check in the voltmeter, the reading is 0.2 volts. So this is the first set of readings we have obtained. In the ammeter it is 1 ampere and in the voltmeter it is 0.2 volt. Now we will change the resistance using this rheostat. So you can see it's decreasing down to 4 units. That gives us the second set of readings. So you can take multiple readings like this and then check the V by I ratio. You will find that the V by I ratio will be constant for all the different sets of readings that we will be taking. Let us now note our observations. The range of our ammeter is 0 to 1 ampere and the range of our voltmeter is 0 to 5 volts as we have seen in the experiment. The least count, that is the minimum reading that can be measured with the help of our ammeter, is 0.02 ampere, while that of our voltmeter is 0.1 volt. Remember, least count means the minimum possible reading that can be taken using that particular device, and the range is like, when we are saying the range of our ammeter is 0 to 1, we mean to say that the ammeter can measure current in the range of 0 to 1 ampere only. It cannot measure current greater than 1 ampere. So the zero errors were not there. So I'm marking it as 0 because both our appliances or both our devices, that is the ammeter and the voltmeter, we checked if there was any deviation before we performed the experiment, but the needle was pointing exactly at 0. That means that there were no zero errors there. Now let us fill in the readings. The first reading that we took on the ammeter, when we corresponded the ammeter to 1 ampere, we found that the voltmeter was showing a reading of 0.2 volt. Since there was no error, so we can just eliminate these two columns. And when we calculate the ratio of V upon I, that is the resistance, we will get a value of 0.2 ohms for the first set of readings. Then when we took the second reading, the ammeter was showing 0.8 ampere as the current. The voltmeter showed a potential difference of 0.5 volt. Again, no correction because our appliances were perfect. So the value of R that we get here is 0.2 ohms. And then the third set of readings that we used, where the ammeter was showing zero point 0.5 ampere as the current and the voltmeter showed a voltage of 0.1 volt. Again, it was 0.2 ohms. So I took 3 sets of readings while performing the experiment. You can go with more number of readings. You can take it up to 6. And when we calculate the mean resistance using these readings, you will find that the mean resistance in this case would be corresponding to 0.2 ohms. So when we plot a graph of V versus I, we will get a straight line graph because as the value of current increased, we find that the potential difference also showed a corresponding increase. So this is the kind of graph you'll get if you plot the readings on a graph sheet where you take current on the x-axis and potential difference on the y-axis. So the conclusion that we can draw from this experiment is that the ratio of V by I is constant. So the current voltage relationship is established, and that is exactly what Ohm's law states, that at constant temperature the current flowing through a conductor is directly proportional to the potential difference across its ends. So Ohm's law has been verified with the help of this experiment. The unknown resistance of the wire that we used was calculated to be 0.2 ohms in this case, and from the graph we came to know that the slope of the graph actually represents the resistance of the wire, which is 0.2 ohms.